Buongiorno, benvenuti a questo incontro.
Good morning and welcome to this meeting, which is titled Knowledge, the Certainty in Scientific Knowledge. It is a topic which poses interesting questions. Is it possible to attain certainty in the scientific field at all, and under which conditions, and in which areas, in which fields can we hope to attain certainty? And also, what is the cultural relevance of this topic? Why are we talking about it at the meeting in Rimini? And why have we invited such an important speaker, a distinguished speaker like the one that will accompany us today, to cover the topic that I will then present? I think that the theme of certainty in scientific insight involves the conception of reason that we all have. It's something that concerns everyone. And this topic of certainty in science identifies some kind of schizophrenic division that we're suffering from because of the mentality we have in relation to science. On the one hand, science is seen, is promoted as the paradigm of certainty. You know, if one thing is demonstrated scientifically, then it's fine. If it is not scientifically proven, then it's an opinion. It's about feelings and opinions. On the other hand, the possibility of continuous and systematic doubts is a determining factor for the scientific approach. Science is the process which can continuously contradict itself, so we will never reach something certain. It's a nonsense to believe that we will reach a reasonably certain point. There can always be an experiment which says exactly the contrary of what we're saying. So there is a dichotomy: on the one hand, absolute certainty, and on the other hand, doubtfulness. As we heard from Constantino Esposito yesterday, this doubtfulness is a strong, typical characteristic of our modern approach. Hannah Arendt says, what in modern age went lost was not, of course, the ability of truth, reality, and faith, and not even the concomitant, inevitable acceptance of the testimony of the senses and reason, but what went lost was the certainty that accompanied them before. On the other hand, in the pathway of science, we do indeed realize that experience shows that it is possible to reach points of non-return, points of reasonable certainty on how things are. 2,500 years ago, the different schools of old Greece were discussing the shape of the Earth. Thales thought it was a flat disk. Anaximanders thought it was a cylinder at the center of the universe. And then Parmenides and the Pythagoreans conceived the spherical shape of the Earth on account of very little data. It was a matter of discussing all this. But think of the evidence, the amount of evidence and cues we have on the general shape of the Earth. Doubting of the sphericity of the Earth today would be like doubting of the existence of the Americas, because one has never been to the Americas. or if we visit the Ulysses exhibition this year, we see Rutherford's example 100 years ago, who, with his experiments, showed the internal structure of an atom, which has a nucleus. Well, this didn't mean that we had learned all about the atom, but that was a real step into the reality of things, a step of non-return. It would seem that through science, man has this ability of saying something reasonably certain and reaching points of non-return. However, these are the questions that we would like to discuss today. What's the meaning of reaching a certainty in a scientific field? What can we become certain of? And which method does reason use to approach scientific certainty? And also, how important is the attitude of the searching individual in order to make a certain achievement? The human being by nature can tell something about reality. These are the questions that we are addressing today to our most distinguished guest. I'm really grateful to him for being here, Professor John Polkinghorne.
Abbiamo con noi uno.
With us, we have one of the most, of the greatest witnesses of the human scientific research in the last decades. He learned quantum physics from Paul Dirac, a Nobel laureate in physics, and he had his PhD with Abdus Salam, another Nobel laureate. I was telling him, and he was very happy to know, that he was the first great scientist that participated in the meeting in Rimini way back in 1982. Please think about this. He's master. In his long career, John Polkinghorne, who is a Fellow of the Royal Society and has been so since 1974, made major contributions to the theory of elementary particles. He contributed at the end of the 60s to one of the greatest discoveries in modern physics, which is the discovery of quarks, the particles which make up the ultimate reality of the nucleus of the atom. This is in line with the exhibition, together with Gilman and Zweig. And among the many responsibilities he's had, he was the president of the Queen's College of Cambridge. But John Polkinghorne is also a theologian, a priest of the Anglican Church. He's one of the greatest scholars in the world for the relationship between science and faith, between science and religion, a topic on which he wrote more than 15 books, many of which are here at our stand in the meeting in Rimini. He was the president of the International Society for Science and Religion, and in 2002 he won the Templeton. He was awarded the Templeton Prize. He will speak about this topic with great philosophical depth, and what is rare, he combines this philosophical depth, this theological profoundness with the direct experience of those that have fought the battle of science and experimentation for many years and at top level. So really, thank you very much. It was my desire to invite him to the meeting. He was at the San Marino meeting 2 years ago, and now he honors us with this meeting. Thank you.
Thank you very much. It's a great privilege and pleasure for me to be here in Rimini again. I'm a scientist, and I wish strongly to affirm the value of scientific insight. But I have to go on to say that I do not think that it is endowed with an incorrigible certainty. We should receive well-winnowed scientific theories with respect and gratitude. But I do not believe we can speak of their findings in terms of an unqualified and absolute certainty. This does not by any means imply that there are not very many aspects of science's account of the physical world that we are right to rely on. After all, I came here on an aeroplane. Whatever doubts that were still lingering at the beginning of the 20th century in pockets of the scientific community about the reality of atoms, concept of the atomic structure of matter has long since come to be a permanent part of our understanding of the nature of the physical world. Yet the meaning of the term atom has been subject to change and development over the years. We do not any longer think in terms of little hard particles with hooks attached, or of a plum pudding of positive charge, in which electrons are the negatively charged currents, or of the solar system atom of Niels Bohr. Today, atoms are understood to be composed of complex configurations of quarks, gluons, and electrons. Very possibly, our ideas of the nature of quarks will in turn require revision. Perhaps they are coming to be understood as modes of vibration of strings of the dimension of 10 to the minus 33 centimeters. So does all this then mean that contrary to attaining a degree of certainty, fundamental science is so continually in a state of intellectual flux that it exhibits a kind of instability that has led its postmodern critics to allege that it is not concerned with discovery, but with socially agreed confabulation, making up pleasing stories. I do not think so, but the issue of what is science's actual achievement is one that calls for care and some subtlety in its discussion. The openness of science, the changing detail of its understanding, has encouraged people sometimes to make the extreme claim that scientists adopt the stance of doubting everything. In fact, such an absolute and unrelenting skepticism would be a very mistaken strategy, inducing frustration and intellectual paralysis. We have to start the exploration of reality by initially embracing commitment to a particular perspective from which to view it. Of course, subsequent investigation may reveal that this point of view is plagued by obscurities and tricks of perspective, so that its revision will prove necessary. Unreasonable unwillingness to think again would be as stultifying to science as would be a relentless skepticism. But one has to start from somewhere. In science, a delicate balance is required between simultaneously both questioning and trusting the present form of understanding. I believe that this is one reason why absolute certainty, the sense of logically unchallengeable belief, is not available even to science. While it is illusory to think that we can proceed by stepping from certainty to certainty, it is equally illusory to suppose that every new inquiry needs to start with a totally clean slate, uninfluenced by past ideas. Einstein discovered special relativity by trusting Maxwell's equations of electromagnetism and showing that taking them seriously questioned received thinking about the nature of space and time. Neither a supine clinging to past ideas nor a restless suspicion of them is helpful to science, or indeed to any human quest for truth. This mixed economy of questioning and commitment lends a certain air of precariousness to the scientific enterprise. One particular source of possible uncertainty is the presence of an ineluctable element of circularity in scientific argument. There are no interesting scientific facts that are not already interpreted facts. Raw experimental readings, that is to say, registrations in counters, marks on photographic plates, things like that, only acquire significance when it is understood or the apparatus being employed is actually capable of detecting and measuring. This active interpretation requires recourse to theoretical opinion. Experiments can confirm or disconfirm theories, but those theories themselves have to be used to interpret experiments. The long-term fruitfulness displayed by a well-winnowed scientific theory, capable of yielding understanding of a wide range of phenomena, and often including some aspects that were unknown when the theory was formulated. As, for example, when my scientific hero Paul Dirac predicted the unexpected existence of antimatter. These experiences strongly support the belief held by sciences that this circularity is normally benign rather than vicious. Yet this trusting stance is an act of motivated commitment rather than the acknowledgement of an inevitable rational necessity. From this fact have arisen the attempts of the postmodern skeptics, which I already noted, to persuade us that contemporary scientific understanding is actually no more than a culturally induced consensus held by the members of the invisible college of scientists, who have simply tacitly agreed to look at things in that particular way. Despite the great implausibility of this claim, I do not believe that it can be disposed of by logic alone. A further subtlety in science arises from the need to exercise certain tacit skills of judgment, which cannot be reduced to the following of a carefully specified protocol. For example, all experimentalists have to wrestle with the problem of what we call background. The need to identify and allow for the presence of spurious events that do not arise from the phenomenon under investigation, but from effects extraneous to it, as for example, when a stray cosmic ray happens to leave a trace in a bubble chamber. There is no little black book or handy computer program which tells the experimentalists exactly how to make the necessary allowance. Dealing with back-row problems requires acts of judgment by the scientist. Employing skills and insights can only be learnt from long apprenticeship in the scientific community. Sometimes these judgments turn out to be wrong. All branches of science can tell warning stories about the mistakes that this can lead to. Equally, theories of deep significance are not simply read out of experiments by a straightforward analysis of the common factors found in a wide range of particular instances, in the manner that was proposed long ago in the early days of science by Francis Bacon. Something altogether more creative is required on the part of the theorist. Strictly speaking, theories that make universal claims are always undetermined by the finite experimental data available. Einstein once said that deep theoretical understanding had to be freely invented. He was too profoundly convinced of the independent reality of the physical world to mean by this a kind of postmodern notion of science as confabulation. Rather, he meant that deep discovery required a kind of imaginative leap, such as that which enabled him in November 1915 to write down, fully formed, the equations of general relativity. Of course, having done so, he had then to work out the consequences of the equations. In a few days, he had shown that they explained what had seemed to be an anomaly in the motion of the planet Mercury, which had long defied Newtonian explanation. Einstein said that this was the happiest day of his life. It was the kind of unforced success that strongly supports the belief that physics really is describing intrinsic aspects of the physical world. Einstein, like many great theoretical physicists, was guided in his search for a new theory by a quest for beautiful equations. Mathematical beauty is a rather rarefied form of aesthetic value. Some of you will know about it, but perhaps not all of you. But it is one that the mathematicians can recognize and agree about. It involves properties such as economy and elegance, and what the mathematicians call being deep. That is, profound consequences are found to stem from an apparently simple starting point. Like all forms of beauty, it is easier to recognize than to describe, and its discernment calls for tacit acts of judgment. Its pursuit is no mere act of aesthetic indulgence on the part of the theorists, but a fertile technique for discovery. Time and again, in the history of theoretical physics, such equations have furnished the key to unlocking the secrets of the universe. Dirac, one of the founding figures of quantum theory, once said that it is more important to have beauty in your equations than to have them fit experiment. Now, of course, he did not mean that in the end, empirical adequacy could be dispensed with. No scientist could possibly suppose that. However, if your new theory did not at first sight seem to fit the facts, though that was certainly a setback, it was not necessarily absolutely fatal. No doubt you had to solve your equations in some approximation. And maybe you had made the wrong approximation. Or maybe the experiments were wrong. We've known this happen more than once. So there was at least some residual hope. But in Dirac's view, if your equations were ugly, well, there was no hope. The whole history of modern physics testified that profound and successful theories are always expressed in mathematically beautiful equations. He himself made his many notable discoveries by a lifelong and relentlessly successful quest for mathematical beauty. This role of mathematical beauty is linked with an important aspect of physicists' experience, the sense of wonder at the marvelous order of the universe disclosed to their inquiry, thus affording them a precious reward for all the labor involved in scientific research. These considerations, I believe, make it clear that science is a subtle activity that cannot claim to attain results to which one might unhesitatingly apply phrases such as certain proof and absolutely indubitable fact. Statements of the kind that an intransigent skepticism requiring total certitude might demand for accepting the conclusions reached. Now, this by no means means that science does not achieve understanding, to which it is entirely rational to accord belief, but simply an act of commitment in that belief is evolved which goes beyond simply assent to the absolutely certain. Time and again, science offers us the best explanation of what is going on in the physical world, affording insights that need to be taken with the utmost seriousness, which prove capable of providing the basis for reliable technological exploitation. As I said earlier, I came here in an aeroplane. In fact, the concept of proof of a logically coercive kind that would defy any possibility of skeptical challenge is a very rare category. And this is true even in mathematics. The greatest logician of the 20th century, Kurt Gödel, showed that an axiomatic system rich enough in structure to contain the integers cannot establish its own consistency by internal argument. And if it is consistent, it can be shown to contain propositions that intuitively can be seen to be true, but which cannot be proved within that system. So you see, even belief that consistency of arithmetic requires an active commitment, admittedly a rather easy one in this case. I believe that the philosopher of science who has been most helpful in discussing these issues is Michael Polanyi. Before he turned to philosophy, he had been a very distinguished physical chemist. So that Polanyi knew science from the inside, with the benefit of long experience of working in the scientific community. He called his major work personal knowledge, because he believed that the tacit skills of judgment needed in science are intrinsically activities of persons, having to be learnt through apprenticeship in a truth-seeking community. And that they could never properly be delegated to a well-programmed computer. The role of commitment in science was very important for him as a basis both for scientific exploration and for trust in the results obtained. Rejecting the stance of a relentless skepticism, Polanyi said that he had written his great book, Personal Knowledge, to show how he could commit himself to what he believed scientifically to be true, while knowing that it might be false. Science is trustworthy, but not incorrigible. We are right to accept gratefully the understanding it offers, not on the basis of a prior logical certainty, but because of the persuasively illuminating insights that it affords. Yet, you might say, is not the point that, although science cannot prove a theory to be true beyond the possibility of skeptical peradventure, surely it can at least show a theory to be false by producing an empirical counterexample. If it does not offer us positive certainty, can it not at least claim a negative certainty? Contrary to the popular saying that one can never prove a negative, for example, try proving that unicorns don't exist, is this nevertheless precisely what science seems able to do? Such a claim forms the basis of Karl Popper's famous account of the logic of scientific discovery. All swans are white until the exploration of Western Australia reveals the existence of black swans, and so the hypothesis is found to fail. There is certainly an important point being made here, but falsification is not as unproblematic as Popper seemed to suppose. For even a very low-level theory, such as the colouring of the swans, there are interpretative issues. After all, perhaps that black Australian bird is simply a long-necked duck. A deep scientific theory with extensive applications and implications will not be abandoned at the first sign of an apparent anomaly. In 1925, a respected American experimentalist, D.C. Miller, claimed to have measured a non-zero drift of the Earth through the ether, in direct contradiction to special relativity. Einstein was unperturbed, telling a friend subsequently he had never taken Miller's results seriously. A self-confidence which, of course, in the event, proved to be justified. Popper's former student, Imre Lakatos, gave a more realistic account of actual practice with his concept of a scientific research program. Such a program is defined by its hard core, the set of basic assumptions which specify the character of the program. For example, the Newtonian program had as its hard core Newton's laws of motion and the hypothesis of universal inverse square law gravitation. The hard core is buffered from immediate contact with empirical data by a belt of auxiliary hypotheses which specify how the core ideas are to be applied. These hypotheses can be adjusted in order to improve the fit with observations without endangering the belief in the hard core itself. For the Newtonian program, these auxiliary hypotheses included the nature and number of the planets in the solar system, and the behavior of the newly discovered planet Uranus was found not to be following Newtonian predictions of the astronomers. This did not lead to the rejection of the program. Independently, John Couch-Adams and Urbain Le Verrier both proposed the additional auxiliary hypothesis, the existence of a further planet lying beyond Uranus, which was perturbing its motion. The subsequent discovery of Neptune constituted a brilliant success in the Newtonian program. Acts of judgment are involved in assessing the persuasiveness of such accommodating modifications. A small discrepancy observed later in the motion of the planet Mercury could not be successfully dealt with by the supposition of another planet, Vulcan, too close to the Sun to be readily observed. As I mentioned earlier, at this point, the Newtonian program had to give away the Einsteinian program with general relativity as its hard core. Occasions of radical revision of the core itself might seem to provide the skeptic with grounds for doubt that the assertion that science is achieving realistic knowledge of physical reality. Thomas Kuhn describes such moments of revision as one's revolutionary paradigm shift, in which the whole character of scientific understanding, in his view, changed so drastically that it produced a deep discontinuity between what had gone before and what had followed. Newton and Einstein were supposed to hold such conflicting views that rational discussion between them would not be possible. This claim of the incommensurability of different paradigms is, I believe, highly unpersuasive, and in fact, it was subsequently somewhat modified by Kuhn. After all, though Newton believed that mass was invariant, and Einstein believed that it varied with velocity, both were speaking about inertia, body's resistance to having its state of motion changed. I think that Newton would have been very interested to learn of Einstein's new ideas and the arguments presented for them. Moreover, a new paradigm has to be able to recover the successes of its predecessor in appropriate regimes. One of the first tasks of pioneers of relativity theory and of quantum theory was to establish what they called correspondence principles, showing how the undoubted successes of Newtonian mechanics could be retrieved as excellent approximations to behavior of bodies large on the scale set by Planck's constant and moving slowly on the scale set by the velocity of light. There is a degree of underlying reassuring continuity present in the unfolding revisions of physical theory. It does not achieve absolute truth, but it can lay a justified claim, the attainment of what one might call verisimilitude, a reliable account of reality on a specific scale. A striking aspect of scientific exploration of the physical world is that quite often the character of the reality revealed is found to be very surprising, proving quite different what prior expectation had led scientists to expect. This fact provides good ground for the belief that the character of science's understanding is indeed induced by contact with the independent character of nature itself. Quantum theory is the paradigm example of encounter with the unforeseeable. In 1899, any competent student of philosophy could have proved that it was impossible for something sometimes to behave like a wave, sometimes like a particle. After all, a wave is spread out and oscillating, a flappy sort of thing, while a particle is small and bullet-like. Nevertheless, as we all know, that is how light was found to behave. About 25 years after this discovery, physicists had to live with the seeming paradox unresolved. A skeptic might have claimed this situation constituted a dismissal of the claims of physics to give a rational account of physical reality. However, the discovery of quantum field theory successfully dissolved the paradox. Quantum mechanics is surely the most successful scientific theory of all time, with a vast range of predictions now known to be fulfilled with exquisite accuracy. Its fundamental hard core lies in what we call the superposition principle, allowing the intimate mixing of possibilities that Newton and common sense would say would never be combined together. In the clear world of every day, there is a state where a billiard ball is here, another where it is somewhere else, there. And those states are quite distinct from each other. In the quantum world, the photon can be in a state of here or in a state of there. But it can also be in other states in which these two possibilities are simultaneously combined in a well-defined mathematical way, which we call superposition. The common sense logic of Aristotle is based on the law of the excluded middle, which says that there is no intermediate possibility between A, being here, and not A, being there. For photons and other quantum entities, a different kind of quantum logic has to apply, taking into account the existence of a range of different superpositions of those classically immiscible states, A and not A. The quantum world is cloudy and unvisualizable precisely because of this counterintuitive mixing. Superposition provides the means for understanding wave-particle duality. In the clear world of Newtonian physics, there can only be states with a definite number of particles in them. Just look and see and count them. But in the quantum world, there can be states with an indefinite number of photons. Superpositions of states with different numbers of particles in them. It can be shown that these are the states which display wave-like properties. That is to say, in more technical language, have a definite phase. The essence of rationality is to seek to conform our thinking to the actual nature of what we are trying to think about. There can be no undue tyranny of common sense, for matters may be quite different from what our everyday intuitions might lead us to expect. The different characters of the everyday world and the quantum world show that there is no universal form that rationality has to take, which could cover both. Aristotelian logic and quantum logic both have their appropriate roles to play. No certainty is exempt of the possibility of revision under the pressure of the way things turn out to be. After more than 2 centuries of splendid success, the Newtonian picture was seen not to be the whole truth. There is also no universal form of epistemology, no universal way of attaining knowledge. Entities can only be known in ways that respect their actual natures. Heisenberg's uncertainty principle asserts if we know accurately the position of a quantum entity, we cannot at all know its momentum, and vice versa. If you know where it is, you don't know what it's doing. If you know what it's doing, you don't know where it is. It's only possible to know half as much in the quantum world as we can know in the clear world of Newtonian thinking. In the late 1920s, biologist J.B.S. Haldane commenting on the discoveries of his physicist colleagues, said that the universe had turned out to be not just queerer than we thought, but queerer than we could have thought. Now the nudge of nature pushing us in counterintuitive directions. The skeptic needs to take seriously the fact that the natural question for a scientist to ask about a proposition, both within science and beyond it, is not, is it reasonable? As if we thought we knew with certainty beforehand the shape that rationality has to take. No one in 1899 had been prepared to believe wave-particle duality to be a reasonable possibility. Instead, the proper question to ask is, what makes you think that might be the case? In this form, the question is open to the unexpected. It does not seek to lay down beforehand the shape that an acceptable understanding has to take. But there will only be acceptance for a surprising proposal if there is motivated evidence offered in support of it. What makes you think that might be the case? Openness to the unexpected is an essential ingredient in the quest for truth. Neither naive credulity nor intransigent skepticism is a helpful stance to take. Science enables us to make maps of the physical world. No map can show every detail of the terrain. In this sense, science's account is always partial and not total, yet reliable on the relevant scale. It achieves a professional degree of accuracy, but not an absolutely comprehensive certainty. I believe that this kind of open but exacting approach to gaining understanding is relevant to all forms of truth-seeking inquiry. We live in a society that seems to have a wistful longing for absolute certainty, a desire to see all questions settled once and for all. Those who espouse such a hope often take science as their ideal, believing that it affords encouragement, the expectation of attaining absolutely certain knowledge. I have sought to show that actual experience of science encourages a more nuanced and modest approach to the exploration of the inexhaustible richness of reality. Even the scientist has to be content to achieve well-motivated beliefs rather than unrevisable certainties. In a word, to live by commitment to motivated belief and not by certainty, by faith and not by sight, you might say. In conclusion, I would like to say that as someone who is both a physicist and a Christian believer, I believe that the quest for religious truth has to be pursued in a similar fashion of seeking well-motivated belief. Scientists are often wary of religion. But they fear that it involves unquestioning submission, dictates of some unchallengeable authority. An infallible book, an infallible community, an infallible person. Of course, they do not wish to commit intellectual suicide, but neither do I. Faith is not a leap into the dark, but a leap into the light. I believe that I have motivations for my religious beliefs of a kind that persuades me to commit my life to them. But that is another story.
You want me to ask a question? Or? You have been so conclusive that I probably don't.
This is like mark up to you.
Grazie, John.
Thank you, John. It was really a very profound account on your experience, a greatly valued one. Science, the understanding in the world of research implies a delicate balance between faith, trust, and quest. Trust doesn't close yourself, but opens one to deep questions, and there's always an act of judgment in recognizing things, also those which emerge from empirical scientific research. The subject is at stake, and dramatically so, in recognizing what appears to his observation of the real. And physics or science in general hardly describes something we have out of ourselves. It cannot describe it completely. Openness, enhancement of reason. Enhancement of reason should be broad. It is reason which, as you said towards the end, allows us to walk towards certainty, also in other aspects of the relationship with reality, not simply the scientific ones, but also within science. No map contains all details of reality, but this is not to say that the map is not real. Without this map, we would not be able to move. We would not be able to have a direction and move in a certain direction. So, concluding this meeting, I would like to ask you another question, John. No. Can you hear me? Can you hear me?
Gli chiedere questo, dopo glielo dico in inglese.
I'd like to ask you, can you hear me, George? Scientific knowledge and this dramatic relationship with reality, where there is a subject that must continuously recognize and adapt his thought or thinking to what is emerging. What is the attitude of the human being? What is the human and rational attitude whereby all this pathway is possible?
I would like to ask, if science, as every other attempt for truth, is this dramatic relationship of a subject, human subject with reality, we have to have that judgment skill anyway,
Yes.
right? So what is the true position, the best possible position for the human being in front of reality to go through this adventure, which is similar to other adventures in knowledge, in human knowledge?
I think the best stance is what I like to call what I like to call bottom-up thinking. That is to say, to try to move from experience to understanding. Not to start with vast, clear and certain ideas, which so often turn out to be neither clear nor certain, but to be taught by one's encounter with reality. So I say I think that is true of our search for religious truth, at one end of the spectrum, our search for scientific truth at the other. But in the encounter with reality, science has a secret weapon which the more personal or transpersonal inquiries into the nature of reality do not have. That is the power to manipulate and repeat circumstances, the great power of experiment. I'm a theorist, but I gradually acknowledge the indispensable role of the experimentalists. So science can pursue matters in a way that can produce pretty wide agreement. In all personal forms of encounter, judging other people's character, judging the beauty of a painting, most of the religious truth, we don't have that manipulative ability. God cannot be put to the test. God's self-disclosure comes as gracious gift, not in response to manipulation. To try and manipulate God is the error of magic, which is a very bad mistake.
Well. Dunque,
so start from the experience. Start from the experience is the way to move towards a certain pathway in the human experience of all. Thank you, John, and thank you, everybody.